Hey guys, how you going? So this video is all about looking at computer systems, and we need to have a start by, if we're looking at computers, we need to have a common understanding of what a computer actually is. So there's a whole bunch of different devices on the screen there, on the slide there. Which of those are actually computers? Obviously there's a traditional PC and a laptop. They're probably relatively easy questions. There's a smartphone, a tablet, a smartwatch, a smart TV, and all sorts of devices like fridges and all sorts of these things now also getting the sort of smart tag. So what does that mean? Are they all computers or are they not computers? Are some of them computers but not all of them? Well, if you haven't decided by now, the answer is, in fact, all of them. All of them are computing devices, and they all have computing capabilities. So how do we then define what exactly a computer is? And good old Wikipedia, whilst it's, Oxford Dictionary in this case, probably gives me what I think is probably one of the better computer definitions around, but there are obviously plenty. And I've highlighted in bold some of the key words in the definition. Then I think this covers all of the different variations pretty well of what a computer actually is. So a computer is obviously an electronic device. It needs to be capable of receiving information, so data, input in other words. We've got to be able to get data into it or instructions into it in some sort of form, particularly in a sequence of instructions. So there you should be starting to think program. Yes, computer should be programmable. We should, as programmers, should be able to write code to make that device do something, do whatever it is we might be wanting it to do. And then obviously, because it's a computing device, it's able to take that input, respond to those program instructions we provide, and produce some output, give us a result. Okay, input, process, output, that basic programming process, a computer should be able to perform those processes. So that's in a nutshell what a computing device is, and certainly all of those things from the previous page fit that definition pretty well, I think. So what we're not going to look at in this part of our course is individual computer components, know about CPUs and RAM, all that sort of stuff. We're more interested in the different ways computers get designed. So we're talking about what we term a computer's architecture. There are different ways, different architectures used to build computers. So when we're talking architecture, we're talking about the components and the way they interconnect. All right? So that's we're not talking about building buildings. We're talking about the way the different components selected for that computer system work, the way they connect, the way they interface with the software to meet whatever the functional needs are for that particular computing device. And there's all sorts of considerations, from how much energy does it use, what does it cost, in determining what's the best architecture for a particular computing device. And now, in modern days, with the array of different devices that we term computing devices, there are different architectures that you can use, and they each have different advantages and different uses. So different benefits in using different architectures for different types of devices in different situations, depending on the goals that we're trying to achieve. So, if I go back, I guess one of the early architectures that appeared was this one called the von Neumann architecture, and this is still very evident today in your what I'd call, I guess, your traditional computing devices. So your desktop and laptop computing devices today still use this von Neumann architecture largely. It was designed in 1945 by John von Neumann. Now, he didn't build a computer. What John von Neumann did in the fairly early days of computing devices, he came up with an architecture, a design essentially, for the way that you would build a computer or put a computer together. A lot of these components didn't even necessarily exist, but he described them. And the big advantage that this computing design, this architecture, had over others that were around at the time was that it used the stored program concept. So in other words, it had this memory capability to keep the program that a computer needed to run in memory so that you weren't having to continually load it all the time. Up until early computing days, the program that you wanted to run was fed in some means, often on punch cards, if you see fairly old sort of computing devices, and that's how the program was loaded into the computer. The concept of keeping a program's instructions stored in the computer is a more recent one, and it's one that really was, developed largely by John von Neumann when he described this particular architecture. And you can see that that's predominantly the way traditional computing devices today still run. We use memory, we use RAM and ROM, we have secondary memory or hard drive most of the time for storage. We have a CPU and other components on that chip that do different things. We have a control unit that directs all of the operations of the CPU. We have input and output devices and a I/O control unit to deal with all of those things. That is still the model that traditional computing devices, desktops and laptops, use even up until now. Very efficient architecture, very cheap to build, which is partly why it was adopted and still is in use, and it's quite efficient, quite an efficient method. Moving on, some issues with the von Neumann bottleneck are evident, and with the von Neumann architecture are evident, and the main one of those is what we term the von Neumann bottleneck. A bit of a term, a bus is a term for a data pathway around which data is transferred in a computing system. Okay, so it's just a pathway. You see circuitry, and there's all those little lines running around those little circuit boards. Each one of those is called a bus. So that's a pathway around which data is transferred. The issue in the von Neumann architecture is that the same bus or the same data pathway is used to connect many different components. In particular, the CPU and the main memory use the same bus. So if you're transferring data in and out of CPU and main memory, they travel along the same pathway, which means data can't run in both directions at the same time. The CPU is also faster than the bus speed. So the CPU can process instructions quicker than what they can be transmitted along that bus or data pathway to main memory and then processed and back again if necessary. So that creates a bottleneck because you've got a CPU having to wait for an available spot, if you like, on the bus to be able to send its data through to main memory. And that's what's known as the von Neumann bottleneck. And the end result is that your CPU is sitting there idle at times, often waiting for an opportunity to send the results of what it's processed. So that's been a significant issue within the von Neumann architecture, and particularly as processors have got faster, that they've spent more and more time idle. So to try and overcome that, computer designers and manufacturers have done lots of different things to try and overcome the von Neumann bottleneck. One of the more earlier, I suppose probably from the early 2000s, I guess, was the concept of multi-threading. And Intel implemented a version of this, they called it hyper-threading. And essentially, multi-threading is actually a software programming technique. It's a technique where you split a program's instructions as the programmer, when you're writing it, up into multiple threads. And you send different threads through different portions of the processor. And a processor was designed to handle multiple threads in software. Intel called it hyperthreading, as I mentioned before. And different threads would go to different portions of the processor and be able to be processed at the same time. It was also all about processing more instructions quickly and trying to handle this von Neumann bottleneck concept. That probably then led to the introduction of multi-core processors. So this is pretty much where we are now. You can't really buy a modern processor that doesn't have multiple cores, even now to the point where smartphones have got multiple core processors in them, and even smaller devices at times. So how can we make a processor process more data simultaneously? Well, another way is to put on the CPU chip multiple CPU cores, so that each one of them can work independently. They combine with the concept of hyperthreading. Each one of them is processing multiple threads from software simultaneously, and it's all about speeding up the processing speed and overcoming this von Neumann bottleneck. So hyperthreading is a software design technique. Multi-core processors is definitely a hardware technique. It's a means by which on the same CPU die, they call it a little chip, multiple cores, so you've got multiple processors in effect running simultaneously. We've also moved into 64-bit CPU architectures as a way of combating the bottleneck. So you can see here in the diagram the 32-bit architecture running the bus between the arithmetic logic unit on the CPU and to memory. 32-bit effectively means along that data pathway you can have 32 bits of data running simultaneously side by side in effect at the same time. Think of it as kind of like a 32-lane highway where 32 cars can all travel down all at the same time, as opposed to the 64-bit architecture where that bus is widened. So the processor is able to have 64 bits of data entering and leaving simultaneously. Think of it as like a 64-lane highway, almost doubling the capacity of what those processors can send and receive simultaneously. And we're now pretty much in the age of 64-bit computing. I think Windows 10 is the first version of Windows, I think, that by default shipped as a 64-bit architecture. You can still get the 32-bit architecture if you wish to, but the 64-bit is pretty much dominant, and macOS has been there for a little while. And most operating systems now, even down into smaller devices, really moving into 64-bit architectures as a way of overcoming that bottleneck and increasing the processing speed and capacity. So moving away from the von Neumann architecture then, and another type is what's known as the Harvard architecture. So one of the great disadvantages of this is that it's expensive, far more expensive to build, and that's why it's not really widely adopted. The thing that makes it more expensive is its increased use of memory, RAM, and that's one of the more expensive components in building a computer. So for that reason, that's its big advantage, but it also happens to be its biggest downfall, because that is what makes it more expensive. But the fact that it's got more memory means that it allows for a lot faster simultaneous processing of data and also program instructions. So those things can happen together, whereas in the Harvard architecture, your processor is either processing data or it's processing a program instruction, not necessarily both at the same time. Harvard architecture, they both can happen simultaneously because they've got their own memory spaces, but that makes the system far more expensive to build. For that reason, you tend to see this design more in things like embedded systems and microcontrollers. So that fridge that I pointed to before with an embedded computer in it quite likely uses a CPU or a computer design using the Harvard architecture. A remote control for something quite likely designed using a Harvard architecture. Very small, tend to be a relatively limited function set and a fairly defined function set, but able to do those jobs really quickly and efficiently because they're using this Harvard architecture. The last one we're going to look at is a more recent one, and that being the ARM architecture. So ARM is an organisation, Advanced RISC Machines, I think is the name of the organisation, what ARM stands for. And ARM don't actually build any processors. They don't build anything. They design CPUs. That's what they do. So they design processors that other organisations or third parties take those designs and actually build them. And in some cases, they might modify slightly and then sell their processors based on the ARM architecture. These processors have become massively popular in mobile devices. Massively popular. So most smartphones and tablet devices today run an ARM, a processor designed on the ARM architecture. That includes Apple and Samsung as the two biggest players. They take the ARM architecture, design their chips and build their chips around that architecture. They pay for the privilege. They pay ARM for that design, which is licensed by them. And they, in some cases, particularly Apple, will add their own touches to that and improve on that a little bit. But this is the dominant processor architecture used worldwide in all mobile devices. Reason being, the thing about the ARM architecture is that it allows, it uses a lot fewer transistors. So transistors, if you know anything about electronics, the way that electricity moves around the system, they're expensive and they produce a lot of heat. So if you can use less transistors, it makes your CPU a lot cheaper to build, and it produces far, far less heat. If you can think about using your smartphone or your tablet, the advantage of it being producing a lot less heat and being cheaper are obvious. It also means your battery life lasts a lot longer. So that's where the ARM architecture really comes into its own in those areas. It also allows you to integrate dedicated controller chips all onto the one CPU. So if you think about smartphones and tablets and things, and the varying different functions that they can perform, like they can have a GPS in them, they can have an accelerometer in them, they can have various other sensors to perform all sorts of different functions that traditional PCs do not have. You might have to plug something extra in to get that functionality in a laptop or in a desktop. In a device designed with an ARM architected CPU, that can be all built into the chip and all built into the device. All of those functions can come in the package without having to plug any extra devices in, and that's perfect for the way the modern smartphone and tablet style device has evolved and what we tend to do with them. We don't need extra devices to plug in; it's all within the unit. So that's why ARM architecture has really dominated in the mobile device market, and most of the big players are using those CPUs in their devices.